Hi friends, so in this video we will discuss univariate method and pattern search method so that you understand univariate method and pattern search method and then we will extend the discussion to our module topic, that is Powell's method. So first uh, we will discuss these two methods. Methods means methods. These methods are used to optimize. That is, we are dealing with minimization problem. So these are used to minimize some objective function, and the nature of the objective function will be uh, unconstrained unconstrained model. Unconstrained model will be given by the examiner. So univariate method. Yes, in this method, uh, we have only one variable at a time. That means uh, we have the general formula of we have the unconstrained minimization problem. Generally we represent like this, that is minimize or maximize. Here consider minimization. That means okay, minimize f of capital X, where capital X is equal to vector x1, x2, etc., xn. This is vector. So these x1, x2 elements, all these are, for example, if we have 2, n equal to 2, then x1, x2 we have. Then we are saying that x1 direction, we have two direction. That means x1 direction and x2 direction. That means this is similar to your vector algebra. That is something like x1 x2 plane. In x1 x2 plane, we have two directions, that is one parallel to x1 axis and another parallel to x2 axis. That means unit vector ax1 and unit vector ax2, right, like this. So we will have two directions. So if x consists of n variables, that means x1, x2, etc., xn, then we have n directions, n number of directions. Okay, now uh, in the univariate method, what we are doing is, in this method we change only one variable at a time, and seek to produce a sequence of improved approximations to the minimum point by starting at a base point xi. That means uh, already we have said that for any optimization problem, unconstrained optimization problem, you should have a initial point or initial value of vector of x, initial value of x, that which is denoted by xi, xi, right? Xi equal to, for example, if the examiner is not specified xi value, then you have to take it as 0, 0, all zeros, right? 0. So by starting at a base point xi, in the ith iteration, we fix the values of n minus 1 variable. We fix the values of n minus 1 variables and vary the remaining variable. That means first, in the univariate method, what we are doing is we have x1, x2, etc. xn, and first we will for initially what we will do is first we will fix this x2, x3, x4, etc. xn values. x2 fix, that means fix uh, values of x2, x3, etc. xn values, and then we will vary x1, vary x1, fix x2, x3. Okay, that means n minus 1 variables. Okay, n minus 1 variables are fixed, and the per- uh, uh, and the remaining variable, that is remaining one variable, remaining one variable, we will vary so that we will get an optimum value for f of xi. Okay, that is what we are doing univariate method. And then in the next step, what we will do is since only one variable is changed, the problem becomes a one dimensional. That means only one variable, say example x1 is varied. Here x1 is varied. So what we will get is we will have some model f of x I. We will have some model like x1 square plus x2 x1 plus x3 x1, like that. Like this, some model we will have. And this x2, x3, etc. xn are fixed value, and we are varying x1, only one variable at a time, that is x1. So what we will get is this problem, the entire problem will is minimized, is reduced to one-dimensional optimization problem. One-dimensional optimization problem. So we have a one-dimensional optimization. For example, this is a one-dimensional optimization problem with x1 degree is square is 2. Degree of x1 is 2. How to minimize this? How to minimize this function is, that is, we know that quadratic function, right? In order to get the minimum for maximum values of quadratic equation, then what we will do is f dash of xi, okay, with respect to x1, then that we will get to 0, and we will again find out f double dash of xi with considering x1 as the variable, and that if there is something like, okay, looks like this, that is, it is greater than 0, right? Greater than 0, that means it is accelerating. So this x1 point, the 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 value of the function corresponding to x1 will be a minimum value, right? So in that manner we will solve this. Solve for x1. Solve for x1. Okay, that is what in the second point we have pointed out, that is, since only one variable is changed, the problem becomes a one-dimensional minimization problem, and hence the base point xi plus 1 is found by one-dimensional methods. Okay, then uh, in the next step, what we will do is the search for the optimum value or optimum solution. Optimal solution means solution is x, right? Optimal solution is denoted by x star. So this is optimal solution. So we will now continue the search for the optimal solution in a new direction. The new direction is defined as the new direction is obtained by changing any one of the n minus 1 variables, and any one of the n minus 1 variables that were fixed in the previous iteration. That means initially we have fixed x. Initially we have fixed x2, x3, x4, etc. xn variables, uh, and we have varied x1, right? Now what we will do is we will uh, we will choose x2 as the variable variable, that means varying quantity, and the remaining n minus 1 variables x1, x3, x4, etc. xn are fixed. Okay, are fixed. So that is what this the search is continued with in a new direction. In a new direction. In a new direction means, yes, we are fixing. Actually, we are fixing in the first iteration. We are fixing x2, x3, etc. xn, and we are varying x1 only x1. So what is happening physically is that, let us examine that. Let us consider x1, x2, two variable. Okay, x is equal to this vector, and if we by univariate method you have to fix the n minus 1 variables, okay, remaining n minus 1 variables, and you have to vary only one variable at a time. That is, we are choosing x1. So that means we are varying x1 means in, yes, in x1 x2 plane, what is happening is that here initially we have 0 0, right, 0 0. Then we are varying this, we are fixing this 0, right, fixing 0, and x1 is varied. Okay, x1 is varied so that f of x is minimum. So suppose x1 is varied to 1. Okay, from 0 is varied to 1. That means it becomes 1 0, right? 1 0 means in this direction equal. Okay, 1 0. So that means uh, we are uh, we are optimizing only in one direction. We are moving the function only in one direction. Okay, by fixing this x2. Now in the next step, what we will do is we fix this x1, right? X1 is fixed. That means we are fixing 1 as it is and varying the x2. X2 is varied. Suppose it is varied from 0 to 1. Okay, then what we will get? We will move in a direction parallel to x2 axis. So in a direction parallel to x2 axis. X2 axis like this. Yes, this is, for example, here it is. What we will get, 1 1 we will get. So we are moving in this direction. That means, okay, that means direction parallel to x2 axis. So that is what the new direction means. Okay, that means the search is now continued in the second step, in a direction parallel to x2, in a direction of x2, by changing the x2 variable and fixing x1 variable. Okay, in our example, and you can generalize this by what if we have n number of variables, then n number of directions will be there. So in one direction, one variable will be changed, so that we will be moving in only in one direction, and all other variables are fixed. Remaining n minus 1 variables are fixed. That means we are only moving in a single direction. Okay, at a time. Okay, at a time. So so yes, in such a way that the function has to be minimized. So, and in the next step, yes, uh, in the next step, the search procedure is continued by taking each coordinate direction. Okay, each coordinate direction in turn. That means we will, in the next step, what we will do is x1, x2, x1, x2, x4, etc. xn we will fix. Okay, values we will fix, and then we will vary x3. Okay, x3 we will vary. So in that way, uh, we will go in all directions in such a manner that we will optimize the function uh, by varying only one variable at a time, or while by moving only by moving uh, only in one direction at a time. That means let me explain this. With this x1 x2 plane, I can move actually. Let me take an example that this is my destination point D, suppose. Okay, and I have a coordinate. I have a coordinate like this. Yes, this destination point lies on a plane that is x1 x2 plane. Okay, and let us imagine that you are here at 0 0. Okay, and go to you have to reach at this destination point. So in univariate method, what we are doing is the person is first of all going in this direction. Okay, and then he is going uh, in this direction. Okay, and then he is going in this direction, and then is reaching to this point, this direction, in this manner. But okay, this is the univariate method. But actually, when you observe this univariate method, the disadvantage of this univariate method is it is complex, because only we are moving only in one direction. We are at a time we are optimizing only in one direction. Okay, but you can observe that cannot you move from this point that, to this point directly, and from this point to this point directly. Okay, this is also possible, but in univariate method, this pattern, or moving in only in one direction, is taken. So that is the disadvantage of this univariate method. Okay, so, or in other way, you can the person can go in this direction first of all, and then he or she can go in this direction, right? So so in so there are a lot of ways to reach this destination. So in univariate method, this, that is, A to B first, then B to C first, then B to C, then C to D, and D to E. So in this manner it is uh, happening. Okay, optimization is happening. Okay, that means uh, in univariate method, by the end of this univariate method, uh, you will you will go in all possible directions. That means if we have x, if x is given x1, x2, etc., xn vector having n number of elements, then the univariate method, you will search in first you will search in x1 direction, and then you will search in x2 direction by fixing all the remaining variables, and then you will go to x3, direction of x3, and then x4, etc., up to xn. In that manner it is going. So it is a lot of time taking process, right? Univariate method. Okay, uh, so we will Now we are going to discuss the univariate method steps to be followed for the univariate method. Okay, and these are the steps. Then yes, that means what we have discussed earlier, that we are writing it as a step so that you will understand better. So first first of all, uh, we will choose an arbitrary starting point x1 and set I equal to 1. The first iteration I equal to 1, an arbitrary starting point. So if the examiner may give a starting point x1, vector x1, some 0 0 0 0 like that, or 0 1 0 1 like that. Okay, or if the examiner is not given, then you have to assume that the uh, arbitrary starting point is x1 equal to 0, all zeros. Then, the next step is to find the search direction. That means in which direction you have to go first. That is SI. SI is equal to 1 0 0 0 0, or this is 0 1 0 0 0. That means 1 0 1 all zeros means it is in x1 direction, and actually this is not 1 0 0, it is 0 1 0 0. So, and in the next iteration, that is I equal to 2, what we are doing is we are moving in the x2 direction of x2. Okay. So you have to take this SI. SI is again a vector, okay, and in this case it is S1. So S1 will be equal to, for first iteration I equal to 1, x1 will be equal to 1 0 0 0 0 up to m, and in the second iteration, that is I equal to, for I equal to 2, that is S2. So S2 will be equal to 0 1 0 0 etc. up to n0, right? And similarly Sn will be equal to all zeros, and the final last element will be 1. That means we are we are fixing all the what all the n minus 1 variables. That means the n minus 1 directions, we are suppressing it. We are okay. We are not going in n minus 1 direction, but we are going in the x, in the direction of xn. That is unit vector axn direction. Okay. So that is what direction means. Now, yes, this is the for I equal to 1 2 3 etc. up to I equal to n, and this uh, if we are not getting the optimized point for the or optimum value for the function f of x, then what we will do, we will again iterate, or we will increase the iteration number, that is I equal to n plus 1, I equal to n plus 1. That means we will again search in the previous directions also. Already searched the directions, we will once again we will check it out. That is that is what this I equal to n plus 1, n plus 2, n plus 3. So the same direction is repeated, right? Now the next step is determine whether lambda I should be positive or negative for the current direction as well. This means find whether the function value decreases in the positive or negative direction. We have formulated only, we are discussing only the minimization problem, right? Minimize f of x. This is our problem. So you have to determine the lambda I, that is lambda I means is the step length, right? is nothing but your lambda means lambda equal to step length. That means in which direction you have to go, that we have find out, and then how many steps you have to move in that direction. That means how many or how much you have to, how far you have to go, how far you have to go in that direction. That is what you mean by step length. So yes, now what is this step is saying that for the current direction SI, okay, current direction SI means current direction initially will be 1, all zeros. So you have to calculate, you have to determine whether the function value decreasing or increasing, whether the function value is decreasing, sorry, whether the function value is decreasing in the positive direction or negative direction. That is what you have to find out. That means that means yes, that means again consider the yes, again consider the x1 x2 plane, right? So first you have to move in x1 direction, that we have already discussed. We are moving in x1 direction, but the thing is whether this direction is true, so that f of x is minimum in this point. That means whether you have to move in the positive direction of x1 or in the negative direction of x1, so that f of x is minimized. That is what our next problem, okay, next concern. So that is what in the third step they have explained. That means find whether the function value decreases in the positive or negative direction. Okay, for this we take a small problem epsilon. Okay, a problem epsilon small problem, or having 1 unit or 1 unit length. Okay, and we will evaluate fy equal to f of xi. That means here f1 equal to f of x1 we will evaluate. That means yes, f of x1 we will evaluate. That means with the given initial, x1 is already given by the examiner, so you will evaluate f of x1, and then you will evaluate, you have to evaluate f plus and f minus, where f plus is f of xi plus epsilon si, and f minus is f of xi minus epsilon si. That means uh, for example, this is the function value somewhere here. Here this is the function value f of x1. Okay, and what we will do is we will evaluate this x1 yes, we are first of all we are considering an arbitrary length epsilon. Okay, and we are multiplying this length to this direction. That means that means epsilon s1. That means like your vector algebra, you have unit vector ax, right? Now you are multiplying this unit vector ax with a magnitude 7. So 7 unit vector ax means it is a vector with magnitude 7 and in the unit vector ax direction, right? So in the same manner epsilon s1 is there. So then we are first of all we will calculate x1 plus epsilon s1, and then x1 minus epsilon s1. These two we will calculate. These two values we will calculate. That means x1 will be here, and we will move in a infinitely small distance in this positive direction, and we will move infinitely small distance in the negative direction, and we will we will find out how the value of this function f of x is changing, right? Okay, and the change is represented by f plus and f minus. Okay, and then we will check whether f plus, the value f plus is less than f1. Okay, then if f plus is less than f1, that means the assumed direction, okay, the assumed direction will be the correct direction for decreasing the value of f. And if f minus if f minus is less than f1, okay, then what it indicates that the minus si will be the correct one, so that the function is decreasing. Okay, then if both f plus and f minus are greater value, then take f1. Okay, fi means here I equal to 1, so f1 we take f1 is the uh, f1 is the minimum value, so that we take x1 as the minimum along the direction s1. Now, yes, so that is what the procedure to find out the direction, so that the function is minimized. In the next step, direction we have find out, right? Direction we know. Then you have to fix how far in that direction you should go. How far in that direction you should go, so that the function is minimized. That means the optimal length. You have to find out the optimal length, lambda I star. Here for the first iteration it will be lambda 1 star. Okay, such that f of capital Xi plus or minus lambda I star xi equal to minimize with respect to lambda I. You have to minimize this function with respect to lambda I in this for this value, that is xi plus or minus lambda I xi. That means minimize this function with respect to lambda I. That is where plus or minus sign has to be used depending upon whether si or minus si is the direction for decreasing the function value. Okay, that means you have to choose a step length lambda I, so that function f of xi plus or minus lambda I si is minimum, is optimal or minimum. Okay, now in the so that lambda I will be lambda I star. Lambda I star means lambda I optimum. Now in the fifth step we will set the new uh, new set of vectors, a new set of points, that is new vector is, that is xi plus 1, and in our discussion it will be x2. So x2 will be equal to x1 plus or minus lambda 1 star into s1. Okay, set this as the new initial point or starting point. Okay, depending on the direction for decreasing function value, and we will get the new optimized value for the function f of x as f2, in which f2 is equal to f of x2, right? Okay, yes. Now what we will do is set the new value for I equal to I plus 1, that is I equal to I plus 1 means I equal to 2 plus 1, that is I equal to 3. We will step and go to step 2. Again we will go to step 2. That means sorry, I equal to s, I equal to I plus 1, that means I equal to, sorry, I equal to 1 plus 1, sorry, I equal to 1 plus 1, that is I equal to 2, I equal to 2. So then what we will do is, we will go to the step 2, that means you have to, again, you have to identify the search direction, that is S2. That means S2 means it will be 0, 1, 0, 0, 0. That means in the direction of X2 we will search, right? We will, that means we will apply the steps in steps in the new direction, which is X2 direction of X2. That is unit vector AX2, right? Okay. So from 2 we will jump to step 3, and then step 4, then step 5, and finally step 6. Then you will get I equal to 3, and also we will get F3, get F3 and F of X3. The new optimized or minimized value, minimized function, okay, function, and the optimum point X3 dot, dot. Okay, so now we will concentrate on this example by you have to solve this example by univariate method. That is, this is our function, nonlinear function, minimize f of x1 x2. That means here at n is equal to 2. We have x1 x2. Okay, x1 x2 equal to x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 square with the starting point. Yes, the examiner has given the starting point, initial starting point, that is x1 equal to 0, 0. Right. Yes, and you have to note this point also. That is, we will take the problem epsilon as 0.01. You have to take the problem, guaranteed problem in all the problems as epsilon as 0.0, or otherwise the examiner will give, will tell you that take problem epsilon as 0.01. Okay, so you need not to worry. And just to find the correct direction for decreasing the function value. Now, yes, that is step 3. This step 3. Right. Now, and then we will use the differential calculus method to find the optimum step length lambda I star along the direction plus or minus si in step 4. Yes, that means, yes, here, yes, this is our problem. X1 x2 is the x plane. We have initially we have this point x0 y0 equal to 0, 0 is given like this. Okay, now this function is f, function f. This is the function f. Okay, function, this is f. Yes. Okay, that means our objective is to minimize this function f. That means first in for the first iteration it was f equal to 20, and in the next iteration it minimized it to 10, and in the next iteration it is minimized to 5. Okay, yes. and finally we got the optimum point here. Optimum point here. So this is the optimum point, means this is f f minimum value, and the corresponding values of the variables will be like this. You project this point to this x1, then you will get x1 optimum, x1 star. You project this to x2, and you will get here x2 star, x2 optimum point. So x1 star, x2 star will be our solution, optimum solution. Okay. Yes. Now, yes. In the for step by step equal to 2. Yes. Yes. This is step 2, and for I equal to 2, iteration I equal to 2, okay, I equal to 2, here we have first, before that, yes, before that we have the iteration, first iteration we are considering, that means I equal to 1. Then by the step 2, we have to choose the such direction s1. So for I equal to 1 we have, yes, for I equal to 1 we have here I equal to 1 we have 1 0 0 0 0. That means here x1 x2, that is n equal to 2, only two variables are there. We have chosen for choose this search direction, that is s1 equal to ordered pair 1 0, is like your unit vector ax. Okay, and the step 3 is to find whether the value of f decreases along s1 or minus s1. That means, so you have to find the direction, whether if you have to go in the s positive s1 direction or negative s1 direction, so that f decreases, the value of f decreases. Then for that we use the probe length epsilon, okay, and we follow the step 3. Step 3 mentioned here, okay, that is, yes, determine whether lambda I should be positive or negative for the current direction si. Okay, that means we will calculate f of xi. That means f of x1 we will, yes, we will find out f of x1, that is f1, that is f of 0 0, that means x1 0, x2 0. That means you have here 0 minus 0 plus 0 plus 0 plus 0. That means f1 is 0 0, right? F1 is 0 0, and f plus is this, f of x1 plus epsilon s1. Epsilon is 0.01. That means x1 we have x1 we have, yes, initial point 0 0, right? So that is f of x1 plus epsilon s1 means this f of epsilon 0. That means 0.01 minus, right? That means this x1 is actually, x1 is a vector, a null vector 0 0. So it is something like epsilon 0 function. This function can be reduced to f of epsilon 0. Okay, now that means 0.01. Okay, wherever you have x1, substitute this x1 by x1 plus epsilon s1. and wherever you have x2, we substitute this x2 by x2 plus epsilon s2. So initially x1, x2 values are zeros. Okay. Then you will get this 0.01 into 1. That means 0.01 minus 0 plus 2 into s, this value. Okay. And f plus you got the answer as 0.0102. 0.0102, which is greater than f1. And f minus you got minus 0.0098, which is less than f1. So it is clear that in minus s1 direction, the f value of f decreases. So we will fix this minus s1, and then you have to find out the optimum length here. To find the optimum step length lambda 1 optimum. For that, s1 we have fixed, it is minus s1 you have to choose. So our equation will be f of x1 minus lambda 1 s equal to f of x1 minus lambda 1 s1 means you have to think like this: x1 minus lambda 1 s1 means x1 is your 0 minus lambda 1, so s1 is your 1 0. So what you will get, minus lambda 1 will get, and 0 you will get, right? So it is a function of minus lambda 1, and right. So that is what we have written here: f of x1 minus lambda 1 s1. Okay, f of x1 minus lambda 1 s1 equal to f of minus lambda 1 0. So this is, so you put this minus lambda 1 in the place of x1 and 0 in the place of x2 in this function. Okay, in this function. So you will this. Okay, that means 2 lambda 1 square minus lambda 1. Okay, that means you got a function f of x equal to 2 lambda 1 square minus lambda 1 So that means it is a quadratic function. Okay, quadratic function, and it will be something like the function f of lambda will be like something like this, right? Something like this. So you have to find out the minimum point. That means you should find out lambda 1 such that lambda 1 give f of x minimum value, f of x equal to minimum. So that lambda 1 can be called as lambda 1 star, lambda 1 optimum. So in this figure, it is this point. This is lambda 1 star, right? Okay. Okay. So this is the minimum point. Okay. So how will you find out this lambda 1 star value? How will you find out? Actually, this function is like a function looks like this. Okay. You need not to confuse. Okay. The function looks like this, so that the minimum value of the function is for lambda 1 star. Oh, this is f of lambda star. X is y. Okay. Now, what is our procedure? What was our procedure? By Newton's method, we have f dash lambda or f dash x. Here, f of x can be replaced as f of lambda. So first of all, f dash lambda should be equal to 0, and f double dash of lambda should be greater than 0. So these two conditions are satisfied, then this lambda 1 yields the minimum value of f. Okay, in that manner we found that lambda 1 equal to 1 by 4, that is 0.25. 0.25 we have found. Uh, so the lambda 1 optimum, that means optimum step length we got it as 1 by 4. So we will get the new point, no new ordinates. Okay, new solution as x2 equal to x1 minus lambda 1 star into s. That's equal to x1 is initially 0 0 minus 1 by 4 and the direction is 1 0. That's equal to minus 1 by 4 0. And then we will find out f2 which is f of x2 and that's equal to f of minus 1 by 4 0. That's equal to minus 1 by 8. So that's the answer. Then in the next step, we will increase the iteration number I equal to 2 and we will uh, repeat the procedure. That is, first of all, we will choose the search direction S2 and that is nothing but S2 equal to x1 is 0, x2 is 1. That means we are going in the x2 direction, direction of x2. Now, f of x2 is minus 0.125. Okay, then in step 3 we will choose an arbitrary length, okay, epsilon, that is 0.01, so that we will get the direction S2, direction of S2 whether it is positive or negative. And S2 is uh, yes, the positive S2. Positive direction of S2 is the correct direction for decreasing the value of f. Okay, that we have found, okay, in step 3. And then in step 4 we have to minimize f of x2 plus lambda 2 s2 such that lambda 2 is optimum. Okay, and so that we will do by your Newton's method, that is df by d lambda 2 equal to 0 and d square f by d lambda 2 will be greater than 0. These two conditions satisfied. If it is satisfied, then lambda 2 will yield the minimum value for that function. So the optimum value will be lambda 2 equal to 0.75. Okay, then we will get the new set of solution, that is x3, that is equal to minus 0.25, 0.75, and then we will substitute in the objective function and we will get the new minimized value, that is minus 0.6875. Okay, earlier it was uh, minus earlier it was anyway it is less. Okay, earlier it was minus 0.125 and here it was minus 0.6875. Okay, actually it is not less, actually it is no, actually it is less only, because minus sign is there, so it is less only. Okay, now magnitude wise it is not decreasing. Why? Because uh, maybe our search direction will not be that much correct. That is the problem of this univariate method. Sometimes you will get a solution or a value of our objective function which is greater than the previous value. So that is what our disadvantage of or a drawback of this univariate method. Okay, then uh, in the next iteration we set I equal to 3 and continue the procedure until the optimum solution x star is 1 1.5. That is, from this minus 0.25 has to be is iterated and it is modified to the new value minus 1, and 0.75 is modified finally to 1.5. So just imagine that how many number of iterations are required. So a large number of iterations are required actually. So that is what that is the main drawback of this uh, univariate method. Okay, and this the optimum value of our model is f of x of x star equal to minus 1.25 is obtained. Okay, so that is what our univariate method. Now the next method is our pattern search method. Okay.